So in the last video, we talked about momentum in classical physics in space. X, Y, and Z, up and down. So what we'll do in this video is think about momentum in special relativity and in space-time. So in space, we have the trajectory of a particle moving through space. In special relativity, we're going to have the trajectory of a particle moving through space-time. So we would want to think of its world line. And in relativity, we've seen that space, x, y, z, and time, t, are part of a unified whole. They're not separate things. And again, as we've seen, observers will have different space-time coordinates. Different observers will have different space-time coordinates for the same event. And they'll differ on t as well as x. So x and t get scrambled up. They're part of a unified whole. So what that means is, for our displacement we're going to think not just through x, y, and z, but also through time. After all, that's right. We're moving through time here on that. So let me write that out. So the displacement would look like something like this. So I'm using a capital letter here instead of lowercase to indicate that this is a displacement, a step through space-time. And so this is a vector that has 4 dimensions. In order to describe the difference between 2 points or 2 events in space-time, I need to tell you their time separation, x, y, and z separation. Usually in this course we're just dealing with that, but at least for the first couple videos here I'm going to keep y and z around as well. So this is sometimes called a 4 vector because it has 4 components. And let's see, so we might have again a v here just to complete this picture. And if we zoomed in, we would have a displacement in space-time, which would have an x part and a t part, and a y and a z part that I can't draw on this flat piece of paper. All right, so then we have a 4 displacement. We can have a 4 velocity. So velocity is going to be displacement over time. But what type of time? We've learned a lot of different types of time. Well, not a lot. 3 different types of time. Well, that's a lot. We've learned about different types of time in this course. So we'll have to think, all right, what time? So the sort of logical, or maybe the thing you might want to do at first is, well, we just divide by dt, because that's what we did here. But it turns out that that doesn't work. That doesn't get us where we want to go in the sense of a new type of momentum that will be conserved in special relativity. I guess there are 2 ways to argue that. One, if I take dx, dy, dz, divide by dt, dt, I'm back to classical momentum, and we've already seen, or I've already mentioned, that classical momentum, this, is not frame independent, or conservation of classical momentum is not frame independent. So dividing by time kind of gets us back to where we were. So here's a way, another thing to think about. All right, so whose time should we take for this? Well, what we're talking about is the momentum of a particle, an object of mass m. So whose time should it be? Well, it should be the particle's time. And the particle's time is a proper time. So what one does in special relativity is one takes the displacement and divides by the proper time of the particle itself. So it's a 4 displacement divided by a proper time. And then that is going to lead to momentum in relativity. So we need to take p, multiply it by m, like we do in classical physics, and then we're going to use this for the velocity. And that's going to be a relativistic momentum. All right, so what are we going to do with this tau? Well, let's remember from a couple units ago that we know how to relate tau to a coordinate time. So here, this is always true because I'm imagining a small delta t and a small delta tau, small enough that the velocity isn't going to change. If a velocity is changing, as this is happening, we would have to do an integral or a sum to add all of this up. That was, there was a long blah, blah, blah about that at the beginning of Unit 4, Unit 5, it all starts to blur. But anyway, this relationship between proper time and coordinate time is true always because these are small steps. And so then this is going to let me rewrite. So I'm going to plug this in for that. And I guess I'll do that a couple of different ways. So P, and this is often a capital P, so I just put a little foot there so it looks bigger, like it's a capital P, is going to be M, the displacement, the 4 displacement in 4-dimensional space, divided by this. And we can think about the components, the different parts of this 4 momentum, this 4-dimensional momentum, just like we did here. In ordinary space, there's an x part, a y part, and a z part. Similar story in special relativity, but now we're going to have a t part to momentum. So the t part just corresponds to that. So the time part of momentum is going to be m. I'm just going to choose the time part here. This is going to be 1 minus v squared dt. And the dt's cancel. So we're going to get pt is just m over 1 minus v squared square root. That's important enough that it also gets a box. Oh, and in a different shade than that one. Sorry about that. And we can do a similar thing for x, y, z. I'm going to write it out just for x because we're not going to use y and z too much, but it looks the same. All right, so the x part of this 4 momentum is I just take the x part of this 4 displacement, this displacement in space-time. It's going to be m dx 1 minus v squared square root dt. All right, so I've got a dx dt. That's the x velocity. That's how fast it's moving in the x direction. So this simplifies a little bit to this. M times the x velocity divided by this square root thing. I will also put that in a box, and maybe in keeping with the rainbow theme, we'll use yet a different color. Okay, so let me recap really quickly. Momentum and special relativity, we think about paths through 4-dimensional space, the world line. A little displacement along that path you would specify in terms of a time, x, y, z. V is dr divided by time, but what time? The proper time, the time of the as experienced by the object itself, which makes sense because momentum is a property of the object, so we should use its proper time. So then we get this. Proper time is given by this relationship from several units ago. So if we plug this into here, we end up with a t component for momentum and an x component for momentum, and also y and z components for momentus. So in the next several videos, we'll unpack this and think about, all right, what does this mean? How do we use this? And what is this form of momentum telling us?